Hey guys, it seems you don't hear anything over the Zoom.
Does this work? This is my local microphone.
Okay, it works.
Okay, yes. Okay, cool.
Thanks.
Yeah, sure. Yes, so just being able to play the game of chess doesn't immediately give you a theory of the game, which we're so interested in. Um,
But don't LLMs, they've read every chess book.
yes.
Ask them what's the theory of this position. Can they answer these questions as well?
Yeah, that's actually a good question. It's related to some ongoing work. Um, they, yeah, they have a lot of useful knowledge about the game that comes from humans like building it and writing it down and so on. But the point here is just that, like it's possible to build an AI that plays the game extremely well and can't tell you what an opening is, right? Like Stockfish is such an example. And it's
So there's no way for Stockfish to even
express that. Yeah, exactly.
All
Right.
we can do is tell you the next.
Yeah, exactly. Right.
So it's just the wrong tool for the job of theory building.
Yeah.
It doesn't mean we don't have tools that do theory. Could do.
Yeah, that's good in principle. Yes. Uh-huh. Yeah, I wouldn't say an LLM is doing theory building because it's at least like not the pre-training and then responding version because it's
So you can imagine an agentic one that you tell Codex,
Mhm.
Try every move that seems reasonable from alpha zero.
Right.
Go a certain distance and give me the broad picture of what will happen with this opening, where you see advantages and disadvantages, which is what humans do.
Yeah, yeah.
Why wouldn't an LLM be able to follow those moves, do a whole lot more of that than I would be able to, report back and say, hey, I think this is a new direction that you should explore.
Yeah. No, I think it's possible and exciting. I'm just saying that like you have to do something for that to happen. Right? You just can you have to build some structure and like understand what would that look like. Yeah.
Sorry, it's might be a naive question, but do you think a tool like Starfish or AlphaZero does not internally have some theory that it's using to sort of suggest the next move, although perhaps it's not able to express that theory?
Yeah, so that's a good question. So I'm pretty positive, and actually there has been some interesting work on this in trying to extract structure from like lattice representations from AlphaZero, for example. And you would expect that somewhere in lattice space it is representing concepts of like, okay, this is that kind of position,
But
this is what tends to happen, and so on. But yeah, it's not in a form that we can immediately just read out and say, okay, this is. But by observing AlphaZero playing some openings, for example, we actually updated our theory to realize, okay, they're actually much worse than we thought. Or like some openings that we thought were bad are actually defensible if you like go deep enough in the lines. And so the French defense, for example, like after AlphaZero is not played at the highest level anymore because people realize, okay, actually it's just bad. If you know what you're for.
One of the things I think AlphaZero was trained on was, an evaluation.
Yes.
function of a
Yeah, yeah.
position. If you have an actual evaluation function, assuming such a function actually exists in the closed game
Right,
test,
right.
then you just literally try every possible move and see which one optimizes the function and you make that move. So you could consider that to be chess theory. And in some sense, AlphaZero has learned that chess theory. But it's not in a form that a human being can, we're not just going to memorize every single positional value and play that.
Yeah, I think it's it's a bit harder to define in general what theory beauty is. But I think when we say theories, we tend to mean something more explicit, like okay, here's a classification and so on, not just like here's the motion, but
But I think the difference here is you want an anthropomorphic representation of the game, which, so we can ask what theory,
right.
but that might actually be a very clumsy way of organizing that information.
Yeah,
That's what worries me more on the grand scheme of things, is that the way our brains have been designed might not be a particularly useful way for mathematics. Right? It's kind of amazing that we've done what we've done, right?
Yeah.
Completely different representations.
Yeah.
And I think along the lines of what Alex is saying might actually be much more efficient. And of course, I would like to understand why things are happening,
right.
but that doesn't change the fact that at least what I'm hearing from what you were saying in theory is something that is the human theory that we as humans.
Yeah, and I agree. And I think part of it is like, what's the point of playing chess? Right? And people like structure and like to understand patterns. So if the point was just to win the game, then okay, we lost, right? Like AI has done that. But it's still interesting because people are still interested in, like in our terms, understanding the game. And yeah, I'll argue that part of the joy of mathematics for many people is in just finding the truth in some sense, right? Like, what's the truth value in this proposition? Maybe that's not most interesting.
Kind of boring.
Yeah, right. But yeah, good questions. And I think chess is and I think it's just one of many other cases of protein folding. Like for many other domains where AI has been successful, you can kind of apply the same argument, for example. So if you look at protein folding and take the problem as being, okay, here's a given sequence of amino acids, how does it fold in 3D space? AIs like AlphaFold have been extremely successful at this problem. But in parallel, people have also been for decades building theories of protein folding, right? Trying to understand what are motifs, like what are the principles that guide protein folding even, and just being able to simulate the process and figure out that the answer doesn't give you the principles, for example. Yeah, so you can make this parallel in many fields in that AI has been very successful at problem solving, but we're still interested in building theories. It's something we still have to do on top. But yeah, so what's the point of building a theory, right? Like, if I can play chess without writing down what are the openings, what's the point of that? Right, so they can get to superhuman performance in many tasks without building explicit theories. But I'll argue that there might be something fundamentally different about domains where you kind of can unboundedly compose components in order to get solutions. So that's the case in mathematics and in programming. In the following sense, if you play a game of chess, you know that it's only going to go for a couple of hundred moves. So the game is kind of bounded in a sense. But if you play the game of programming or the game of mathematics, you actually don't really have like an a priori bound on how hard a solution can be to a given problem, right? And in that case, I think theories actually play an even more important role. So here's an example from programming. Can AI create a website? And the answer is definitely yes at this point, right? Like it's very easy to do so. But it's only easy to do so to solve this problem because the theory behind the solution already exists, right? We have already built browsers, JavaScript, HTML, libraries, CSS works, and so on. So the solution to the problem of creating a website has a few hundred lines of code, but not billions, which would be the case if you had no theory at all of what the website is like, in the sense of I had to describe, okay, I want this to happen when I look at the screen and so on, and there's no browsers, they're just like assembly code, right? Then suddenly this problem becomes extremely hard, right? Like infeasible to for any search algorithm or any generative model to tackle it. And that is likely the case with lots of open problems in mathematics. So when you say, "Hey, can I go and think hard and come up with a solution to the Riemann hypothesis, for example?" The answer is no, and probably because we just don't have the theory enough developed to be able to tackle that yet, right? So there's this pragmatic sense in which theory building is often an enabler of problem solving, at least for these domains of mathematics and programming, for example.
After that also.
Yeah.
In mathematics, we don't know what the goal is.
Mhm.
In chess, you know what the goal is.
Yeah.
That's what the theory tells you,
Mhm.
what their goals are.
Yes, that's another difference of
So in the problem solving, we already have like individual goals then,
usually is, yeah.
that's like.
Yeah, problem solving, you gotta go.
Yeah.
Here's a goal.
And the theory creates goals that you didn't even know were there.
Yeah.
I mean, just to be devil's advocate for what you said
Yeah.
about the Riemann hypothesis.
Yeah.
You're probably correct, but, you know, it could be that we already have the tools. We just don't know how to align them at the moment, or we don't know how to align them efficiently. So let me to give a concrete example.
Right.
I mean, I think, was it squaring matrices or multiplying matrix again, it's a vector where Google, multiplying matrices, right? So they learned a better method to do, right? Okay, we've had a lot of work
Yeah.
that we've done and theory to multiply matrices. And it turned out that, again, putting AI to it gave us a better answer. So even something like this, you know, it's saying what the tools are, the theory is, it's quite possible that just going back through that theory that we already have could produce something that's much, much more efficient. Maybe not to our liking,
Right.
or to our ability to communicate about it.
Yeah, I think it is possible. Like it's plausible that there is some clever combination that we just skipped. But the more and more people spend time on this, on these open problems, the more.
No, I was taking it extreme, but just to point out that.
No, yeah, for sure, it's definitely possible. And I think it would probably be an even more surprising result. Right? The answer was kind of already there in some combination. But yeah, so there's this pragmatic view that for open problems, we might have to build new theories in order to be able to tackle them. And there's just aesthetic view that I think it's an interesting thing to think about. Like it's a thing that humans do, we're interested in, and we should think about it. But okay, so problem solving in a computer is very easy to specify, right? Like you have some tools, we're talking about math, some definitions, some lemmas, some tactics. You have to combine them in order to close your goals. But what would theory building even look like in a computer? Like how to represent theories and so on. What makes a good theory, right? What's the objective function for building a theory? And this is not all that a theory is, but at the very least, a theory is generally composed of abstractions. In mathematics, for example, these abstractions are definitions and lemmas. And abstractions are generalizations over concrete things, right? Like so in chess, when I say an opening, I'm saying like a very large collection of positions that I kind of classify in a certain way, tactic motifs or some kinds of abstractions, patterns in protein foldings are abstractions. So core to a theory is this collection of abstractions that kind of build on each other. In Linear, for example, if we're talking about a formal theory of mathematics, we can include definitions and lemmas, for sure. We can also include tactics, which are a kind of abstraction that we use to build proofs, right? So that's one other kind of abstraction that's important for a formal theory. Foundationally, we know that abstractions are not generally necessary if all we care about is being able to represent in principle the things that we want, right? So if we want to represent mathematics, we don't need abstractions, we just need first order logic and ZFC, right? And we can prove things about mathematics in that way. So they're not required for representation, but they're required for having small representations. So it is known in proof theory, for example, but not too hard to see why that introducing abstractions can have an effect of being able to represent the same symbolic terms with exponentially fewer symbols. Because if you don't have abstractions, every time you reuse something, you have to kind of inline it. Like you can write a program without functions. You just inline all the functions every time you would like to call them, right? But it's clear that your code will grow very ugly if you do that. So here's one hypothesis that we can start to work with computationally. That the point of abstractions and theories is to be able to compress knowledge. And again, compression is something that's slightly more tractable than theory beauty. So here's one example, or just a sketch of what this would look like in logic. So let's say that I have a set of mathematical propositions that I know to be true. And so they follow from some theory T, right? I have proofs of each of these propositions. So the point of building a new theory, T prime, would be true. But hopefully I'm not adding any new assumptions. So I'm just deriving things that I know to be true from what I know. But I can try to find a theory T prime that where if I prove the same statements from T prime, I get much shorter proofs or simpler by some metric. And the complexity of what I added to T prime is also not very large. So maybe I would find a better theory by minimizing a combination of these two things, the complexity of what I added and how simply can I represent what I knew before. So this is one version, compressing proofs in order to find maybe lemmas that help me represent those proofs.
When you're talking about length of proof, you're doing like a homograph kind of thing, like the smallest possible length of proof that you could possibly conceive of in a non-computable way, or do you mean a specific proof is shorter?
Yes, I mean a specific proof has fewer steps with what's the right complexity metric for proofs is still open. So like just the size is maybe the first pass. It's like number of steps. But yeah, so this is about compressing proofs. But interestingly, if we compress the theorem statements and not the proofs, what we'll get is definitions that help us represent those statements in a simpler way. So here's an example. If I have a set of these two propositions, one is there exists k such that true k is 10, and the other is a slightly longer quantified statement. They look long, but one way to compress these terms is if I introduce this new definition, even n, and rewrite the statements to use this new definition. So they're equivalent, but now they're much shorter, right? So now the same statements can be represented as 10 is even and n is even implies n squared is even. So here's one computational story for where definitions could come from, right? They could come from compressing theorem statements, for example. So this problem of symbolic compression has actually been quite widely studied in yes.
Okay. When you're coming up with definitions, that's not the metric that matters. Whether you can compress P is whether all of your P's combined with the definition is shorter than all of your P's without definition.
Yes, right. So I would have to take into account the size of the people, but in this case, it does fit. All right. Yeah. Yeah, because just trivially, I could replace anything with a definition that has the same thing, right? But here, since even appears 3 times, it is worth it. But okay, so this problem of symbolic compression has actually a quite long line of work in the context of programs, in program synthesis. Mostly in the n-type lambda calculus. So in this world, a program is formed by this very simple grammar. You have variables, you have lambda abstractions, function application, and constants that come from represent things in your domain. So for example, if I'm writing programs about lists, I might have primitives like the empty list, ways to construct lists and extract elements from them and so on. And here, the semantics of lambda calculus is basically given by this evaluation relation. We substitute arguments when we apply lambdas to arguments and so on. And foundationally, the lambda calculus doesn't have a notion of a library, but this is something you can introduce. Just say that the library, as known as this literature, is just a finite set of abstractions that are given names to them. So they're all lambda abstractions. And so in this world, programs are just lambda terms in this lambda calculus, and libraries are collections of lambda terms that have names that I am allowed to reuse. So one problem that that is very useful to look at from this literature is this problem of what's called library learning. So we not just using a library just to find programs, but actually learning what the library should be. So this is done as follows. So let's say that I, in some way, came up with these two programs to maybe solving problems in a particular domain, like list manipulation. And the first program here takes the list Z, takes its first element and then adds 1. And then the second one forms a list with a single element 1 plus 1. So these programs don't have abstractions, they're just expressions, right? That compute a number in the left-hand side and a list on the other. But one abstraction can be learned from these two programs if we try to generalize the subtrees that appear here in these two programs. So essentially, we can refactor by compression here by defining this new abstraction plus 1. It takes an element x and adds 1 to it. And this will lead to these two updated programs. If I then go back and use the abstraction to rewrite the programs, T1 prime and T2 prime. So
I like to say, so you're saying, just look at, let's say, because we currently have this problem in formalized mathematics in general, like I spoke about yesterday, where we have lots of formalizations, and we want those formalizations to get good enough to go into the math library. So it's like some canonization.
Right.
And so what you could do is just generate all of the proofs willy-nilly, and then look for subgraphs in that proof tree that are isomorphic, or LLMs might be able to say this is a similar argument, and just compress along those, and just follow that until you can't compress anymore, and that's the theory.
Right.
That's
the principle we can follow.
So take that red subtree, collapse it into a single node, reuse that node.
That's it. So basically, so Dreamcoder is a version of that was proposed for program synthesis a few years ago. We'll be taking a lot of inspiration from this work, and what it solves is essentially this problem of if you have a corpus of programs, you can algorithmically find an abstraction A that minimizes this combination of the size of the programs after refactoring with the Z abstraction, and like a penalty for the size of the abstraction itself that introduced. It turns out that in the n-type lambda calculus, you can do this extremely efficiently, like it scales for tens of thousands of these programs. Right, so
this software that's usable today?
Yeah, it is. Not Dreamcoder, but the successor of it, Stitch, is very usable in the n-type lambda calculus.
Can we turn it on the prime number theorem project and have it refactored for us?
We could try it, yeah.
Beautiful.
Yeah. I'm skipping ahead a little bit, but I'm working on an extension of this for dependent types so that we can try exactly that. Yeah, we have to chat about that. But yeah, so we can try to balance this corpus compression and the abstraction complexity, and refactor so we can take a very good abstraction, refactor the corpus, and then repeat, right? Now we have slightly smaller programs, but we can learn the abstractions, and maybe they'll start depending on previous ones as we iterate this. So in the context of programs for a wide variety of of domains, the encoder was able to start from extremely low level primitives. So here, list manipulation programs. And then by repeating this procedure of you try to solve tasks, you find a few programs, you compress them, introduce a new abstraction in your list, in your library. And then now your search might get a little bit farther ahead in solving those problems. You try it again, you keep learning these abstractions. What they found is that you actually end up reconstructing a lot of very human readable abstractions that we would have in human libraries if we were to write them. So if you start from list manipulation primitives, you discover fold, and then map in terms of folds, and then zip in terms of range and map and so on. So this maps very nicely to abstractions that we can understand. And it's easier to see also why these abstractions actually help in problem solving, because if you take one task that Dream Coder is able to solve, if you were to just write it in terms of primitives, this would look like this. Right? So like search finding something like this is very hard. But if you have the right abstractions, then this is the perfect zip A minus B. So very easy, right? So you would expect with the right library, it's a very easy problem. Without the right library, it's like almost intractable.
Sorry, one last question.
Yeah.
So I understand that in the context of me,
Mhm.
an abstraction would be like a new definition.
Mhm.
Would you say a tactic is also an abstraction in this case?
Yeah. So I think it is.
So if you have like a bunch of proofs in which it's the same proof strategy, like
Mhm.
whatever you divide by two on both sides,
Right.
you can sort of make that a tactic, and
Yeah.
that reduces proofs length.
Mhm. Yes. So in a couple of slides, we'll be talking about doing exactly that. Tactic induction.
Sorry, I think I missed something. What is free coder?
Yeah, so Decoder is this paper from 2021 on programming synthesis. So it's trying to solve programming problems, basically this kind of programming problem, where you have a few input-output examples, and you're trying to find a program that behaves in that way. And the key idea in Decoder was not just learning to solve problems, but also introducing this abstraction learning step. So
It's a program itself, or it's an LLM, or
it's a program itself, no LLM. It's three elements. Right. Yeah, so it's training your network to guide search, but it's like a small, just use it as a heuristic.
It's a great way to illustrate, the top is Rothendiek and the bottom is Erdős.
Yeah.
So Rothendiek also wanted to solve problems. He didn't just want to build theories.
Yeah, exactly.
The way to solve problems is
Mhm.
to build theories first, and so problems just trivially fall out.
Mm-hmm.
Whereas Erdős would be looking for something extremely
Mhm.
clever,
Right.
hard to find.
Then you find it, and okay, next one. But yes, very much so. But okay, so far we've been talking about programs. But we like mathematics. But nowadays, more and more of our mathematics is represented as programs. So if you look at the graph of the growth of mathlib in Lean, for example, yeah, there's a lot of mathematics that has been encoded essentially in a programming language, right, in Lean. But since we know about compressing programs, what here?
there.
Oh, here. Oh, there might have been a refactoring that's shaved many lines at once. I'm not sure. It's a good question. Yeah, right. Yeah,
That's like 200,000 lines of code disappeared.
yeah.
Oh, that was the day they stopped. There was a port from Mathlib 3 to Mathlib 4. Had all this forward and backward stuff.
Mm,
And look at the Mathlib 3 line is done.
yeah, that's
So
right.
that's the day they're like, okay, Mathlib 3 is done. And they dropped all that from Foundation.
Mhm, mhm. Yeah, so now we can ask, right? What would compressing these programs that represent mathematics?
I guess that graph does show that counting lines of code is the wrong way to do it.
Yeah. Yeah, we're looking for better ways. But um but yeah, so we know about this correspondence between programs in a particular functional language and mathematics, right? Called the Curry-Howard correspondence. So we can see mathematical propositions as being coded as these types in a suitable language, proofs as programs that have those types, and both of them as lambda terms essentially in some lambda calculus that's expressive enough. So since we know about compressing lambda calculus, then what does that give us? Well, that gives us that compressing proof terms would give us lemmas that help us express those proof terms in a shorter way, right? A lot of proofs are not written, for example, in as terms, right, but as tactics. But if we compress tactic proofs, then that should give us new tactics, right, that simplify those proofs. And if we compress types that encode propositions, then that should give us definitions to simplify the statements themselves. So there's this nice bridge that connects everything we know about programs to everything we know about mathematics. But okay, so I became interested in this problem of inducing tactics during my PhD a few years ago. And one of the, again, pre-LLMs, so one of the case studies that we conducted to study this problem was trying to solve problems from Khan Academy. So essentially, we formalized these 5 sections of Khan Academy algebra, and we tried to train a model from scratch that would learn to solve these problems in like a small proof system. And the first thing you would try is reinforcement learning, right? Like we have a reward function. Did you solve the problem or not? It's easy to define. You have some axioms that you can apply. Can you just do RL and learn what actions to take to get to the reward? In principle, that's something you can do. But we showed how this idea of library learning actually overcomes one fundamental limitation of RL in these, again, these like very compositional domains. So first of all, we just formalized these problems in a small theorem prover. We created problem generators from templates from the platform itself so that we can get an infinite number of problems from each section. And we encoded them in a theorem prover that has a finite action space. So you can, in principle, just search for combinations of axioms to find proofs and try reinforcement learning, right? But if you do that here, what happens is that you eventually learn to solve problems from the first 2 sections of Khan Academy. The agent gets very good, but you can run it for days and you'll see no progress at all in the next 3 sections. And that happens because as you go from section to section, in terms of the starting axioms, the solutions are getting longer and longer. And reinforcement learning alone depends on this ability of exploration to give you some signal, right? At some point, you should try something random that works, and then you start to repeat that. But if the solution starts to get too long to even do the most basic problems, then you never get there just by kind of trying random actions. But of course, humans learn Khan Academy, right? So it has to be possible. And what we noticed was that if you look at the first 2 sections that were successfully solved and look at the solutions, you'll see a lot of similarities between patterns that appears in these solutions. And in fact, in this representation that we had, that is where all the solutions were straight lines, just applications of axioms, there's again a nice compression algorithm that you can apply here called anti-unification that essentially takes these segments of solutions and tries to find abstractions of them. Like if you substitute maybe a constant here by a variable, you can maybe unify it with another solution. And those essentially give us tactics, which we can discover with this anti-unification procedure. In the sense of like a tactic being a sequence of actions that I can still apply in my original environment, but maybe with different arguments. Oh, it's because it's the inverse of the unification problem, where if you have 2 expressions, you're asking if there's a substitution of variables in the expressions that makes them the same, that unifies them. Anti-unification is you have 2 different expressions, and you're asking, is there like a higher level expression that can become them if you substitute? Yeah. These are 2 problems in first-order logic. But yes, so basically we can apply a very similar move to encoder, where we do reinforcement learning, learn to solve some problems, and then we look at the solutions, try to compress them, and add those new abstractions as new actions that the agent can take. And if we combine that with reinforcement learning, then we make progress and eventually are able to solve all the problems from Khan Academy. But more interestingly, the tactics are, again, very simple procedures. We can look at them and see if they make sense. And we see that they actually match what we would expect students to do on Khan Academy in terms of like how the solutions look like when they express them in terms of these tactics. So if you had an equation like x minus 9 equals 3, for example, you wouldn't expect your student to be applying commutativity and associativity and reordering terms and so on, and give you like 20 lines of code, right? We would expect something like this, like you add something to both sides, and then you simplify on one side, and then you calculate on the other side. And that's exactly the kind of structure that the tactics here recovered. For the last section of those of that curriculum that was called two-step equations, for example, there are only two steps if you have the right two steps to apply, right? Otherwise, in terms of the axioms, there were like 20-something steps. And the agent, once it's able to get there, it actually finds the two-step solutions that Khan Academy was expecting. But one interesting thing that you can also do here is we can infer from the tactics what the order of problems should have been based on the dependencies between these tactics. The agent was just seeing random problems in a random order, trying them and escaping when it failed. But after it has all the solutions, we can look at the dependencies between tactics to induce what consistent topological orderings of the problems would be. And that gives us a curriculum, right? And we can see, okay, does that compare to the Khan Academy curriculum at all, or is it just a crazy ordering? And we see that largely you get the high-level structure of Khan Academy just by looking at these dependencies between tactics. They're much more fine-grained, which might be good or bad pedagogically, but roughly speaking, you can reconstruct what the sections should look like. But okay, so that was in this kind of toy proof assistant. But can we induce tactics in something slightly more complicated, right? Where solutions might not be straight lines, for example. So in this work, that was a collaboration with folks at UT Austin. We did that for Rock, which is maybe level 1 of this game. Lean would be level 2. So you can be a lot more creative in writing tactics in Lean because of metaprogramming. But even in Rock, there are already a lot of complications that get added here. So for example, tactic proofs in Rock are not necessarily straight lines, since proofs can have branches. But also, the branches are not independent necessarily, because you can have, for example, existential variables that are shared between branches, and an action in one branch can change what happens in another branch of your proof.
Branch in the proof is when you have multiple goal states?
Yeah, right. And you can have multiple goal states that are tied by these like existential variables that are delayed.
One branch is specify what the variable is, and another branch is prove that the variable does.
For example, yeah, exactly. Right. Yes, and also in Rock, syntax just like anti-unification is a very syntactic procedure. Like looking for substitutions of this, it turns them exactly the same. But here, syntax is a much weaker guide because there are lots and lots of different syntactically valid ways to write essentially the same proof. So we don't just want to be looking for exactly like the same text. But one idea that we found here is that, well, a better representation for proofs in Rock is as a sort of graph that captures essentially the data flow in the proofs. So we call that the tactic dependency graphs. And we build these TDGs not by looking at the proof statically, but actually by executing the proof and tracking what goals are, what hypotheses they're taking, and so on. So here's one example. You can have these two different proofs for whatever theorems, doesn't matter too much. And if you look at them a little bit carefully, you see that they have a little bit of shared structure, but it's not too easy to see. But it's actually very easy to see once you represent them as a tactic dependency graph, actually you get exactly the same graph, even though the proofs as written are very different. So TDGs allow us to see these common data flow patterns between proofs. So here are two different proofs, for example, for different theorems. But they both have these patterns that are colored here. I'll go a little bit faster just because of time. But once I represent these two proofs as these graphs. What I'm able to see is that there are some subgraphs here that start to look similar, right? So there's like red feeding into rewrite multiple times. And what we can do to find tactics here is to look for these isomorphic embeddings of subgraphs between these two TDGs. There are extra conditions you need to be able to find valid tactics. These graphs have to be collapsible in a certain way. Like isomorphism in principle doesn't care about connectivity, for example, right? But I can have a tactic that will be applied here, then disappear, and then do something and go later there. So I have to have some extra technical conditions for this to work. But essentially, if you do that from these two graphs, you can induce these two tactics that will correspond to the colored subgraphs there. So one is this pattern of simplify and then rewrite. And another is this destruct and then unfold and do something on both branches. And then having these tactics, we can then go back to the original proofs and rewrite them to now use these tactics. So they're slightly shorter.
When you said there's technical issues, I mean, is this more than arguing that you've done topological sort on this, so there's no cyclicity anymore, so it's really a partially ordered set. Are these collapses sufficient to say that these are pulsed morphisms, or is there more that's necessary? Yeah, the harder condition here is that there should be no path between, that's maybe it's easier to illustrate here. There can be no path between something that's created inside the tactic and that reaches another node in the tactic, but passing through something that's outside of the tactic. If that happens, that would mean that you created a variable inside the tactic, it's used somewhere else in the proof, maybe modified, like a go, for example. Exactly. Lose the order. Yeah, right. So that's like the collapsible. Yeah. But essentially, that's the idea. Yeah. Okay. So if we do that for proofs in Rock, we end up finding actually lots of kind of simple ways to compress human-written proofs. So these are not LLM written. And in fact, if as we had hoped originally, if we now use these tactics, like in context, for example, for a prover that's trying to prove theorems in these domains from these repositories, we do see that these are helpful. So LLMs can take the tactic in context and kind of realize when to apply them and so on. And the problems become easier, right? Because now you have less steps to predict. But if you look at the tactics, okay, they're useful in practice, but they're not still conceptually super interesting. So they're like maybe kind of small local strategies that you can apply. But yeah, we still need work here to be able to actually get interesting tactics like ring, for example, from seeing lots and lots of solutions to problems in rings. We don't know how to do that yet. So do you think that's going to require something fundamentally different, or just, I mean, if you reapplied now these ideas, given that you've already in some sense provided simplification? Yeah. I mean, is that your hope that just doing this on nested levels will get you to something like a ring, or do you think you're fundamentally still missing something? Yeah, I think there's some pieces that are missing. So for example, one thing here that is missing is we can only unify these solutions that apply exactly the same strategy. But for something like ring, you would expect that if you have a particular equation that you're solving, you might go one way, right? And for another situation, you might go another way. But there is one general way in which you could solve both. And that's not visible from just seeing those two particular things.
So this wouldn't find ring.
No, no. Yeah, agreed. You did new ideas there.
What about, maybe at the first level it finds some very crude ring, and then the next level it sees, oh, all of these things that are checking algebraic equations are using combinations of the rings
Right.
like a maybe second and third order,
Yeah,
acted through this same process. Maybe, you know?
we could try. Yeah, I think it's a worthy goal to try. Yeah, I think at least for now, you might have this problem that as written, the solutions are not this like using the same techniques. But there is this more general way to be able to solve the problems.
I mean, ring and linear are both based on theorems. So, I don't know if that helps. An LLM, it might help an LLM dream up that these things are
Right.
but how do you
Yeah.
say just in the graph structure?
Yeah, right. Yeah. But yeah, so also this is like purely symbolic approach, but it will also be very interesting to maybe combine it with elements, like I said, we can look at situations and say, okay, propose generalization.
I mean, okay, I won't easily be wrong here, right? But I mean, MATLAB is trying to keep everything as simple as possible, right?
I think it's trying to do very much this kind of thing.
No, I'm thinking of the MATLAB library.
Yeah.
It's, everything is supposed to, it doesn't want lemmas or theorems in there, right? Because it wants to decompose things so it's as reusable as possible. Okay. Now, there's a lot of work being done, right, to prove theorems. So that theorem is not itself going to appear in MATLAB. But there's going to be lots of instantiations of theorems that have been proved using the MATLAB structure. So that becomes, I think, a nice database to try to do those experiments, right? Because there will be very complicated math results that have multiple instantiations of the same kind of math result. Okay. And then if you go back and look at what are the pieces that were used and try this iterating this again multiple times, which is I think what you were suggesting, you might actually have a database there to try to do that. Does that make sense? Or maybe that was just what you were saying.
Yeah. You want to try this out?
Yeah, we're fine. Yeah, no, but yeah, I think that's a really cool goal. But yeah, so I mentioned very briefly, I've been doing a little bit of work on basically porting this that has worked well in untyped lambda calculus to dependent types. So the idea is to have like a G encoder like library learning for that you could apply in Lean, for example. And I think that would be true interesting applications of this, right? Like you could use it on existing human developments, maybe interactively, maybe in batch. But it would also be very interesting to use this in the kind of conjecture improving loops that folks have been playing with. I have some work in that as well. In that you have models like maybe making conjectures, writing proofs, and then trying to simplify those, right? And we think looking at the abstractions that would be discovered in that way would be really interesting. But yeah, so like if you take all of MATLAB, that's a lot of mathematics, and I'm sure there's like lots of interesting new ways to find compressions of that, right? But yes, okay. So I had another project that is not going to be described in a lot of detail, but I'll just try to give it a gist. Yeah.
If you were to run a graph mining thing on Lean, do you run that on the truth literals or the abstract syntax tree of the Lean compiler?
Yeah, so for Rock, we actually executed the proof, and got like a trace of all the proof, all the states basically, and try to match like, yeah, hypothesis and like, yeah. But it was important to not just rely on syntax. like even the IST would be true.
Yeah, it would be. I just thought, something better in way to try that graph mining strategy on.
Yes. Yeah, but I think we need a lot more just like remembering the convenience. Makes the problem in general harder, but also gives you more flexibility in how you can write type it.
Can we like run that program on our personal computer?
You can, on Rock, like you do run Rock, like you do run Pop Top and random versions of it. They don't like out of the box work in me, but we can work through it.
Alright, thank you.
But yeah, Tech Miners on GitHub. You can write. But yes, so essentially this other work, which is related to theories, but in a more indirect way, is just trying to solve the problem of data scarcity in the sense that we want to train good problem solvers. Formal problems are posed in some theory, right? So like proven some T given some definition and so on. So for AI to be able to learn to solve problems, we need these pairs of like, here's a theory, here's a problem. But many problems in formal reasoning end up with this regime that we don't have that many examples of human-written theories to even pose problems right? So for example, in program verification, a theory is given by a program besides the library. And if you look at programming languages that support verification, people haven't been as excited in writing programs in them as in Python, for example. So we have a lot fewer examples of what these pairs look like in Daphne, or if you come up with new cool tools or languages, by definition, they come up with 0 examples, right? Maybe a couple that are read by hand. Or problems like, can you formalize this paper? We don't have that many pairs of like paper and formalization yet. But we do have these quite good generative models that can try infinitely many times. They don't get tired. And we have verifiers, right? So in principle, some combinations of these two should give us an infinite number of theory problem pairs, right? To be able to learn and train.
As of a few weeks ago, we have examples of, blueprints, LaTeX blueprints, with 200,000 lines of clean code that solves it. So how much data would you need before you can start learning?
Yeah, that's a good question. So far, it has been a bit hard to say how many examples you need, but the answer always seems to be you don't have enough examples yet. For language models that keep getting larger and so on. But yeah, it's definitely a lot better of a situation than a few years ago, really. And yeah, so I'll summarize in 1 minute, so don't hope to understand much here, but essentially, I've been looking at this problem of, given that we have these two things, LLMs and verifiers, can we just generate an infinite number of Daphne programs? So Daphne is like this language where it can have specifications, tries to prove the specifications for it by itself, but it often fails, so you have to help it by adding like things like loop invariants and assertions and so on. And then it succeeds. And if we want a language like Daphne to be very easy to write, then ideally people wouldn't have to care about, okay, I have to specify my loop invariant and so on, right? So maybe that's something that AI could help with.
Sorry, what's the difference between Daphne and Lead? You can specify programs.
Yeah, you can. So Daphne is more focused on automation. So it's harder to prove things by hand in Daphne. It will always try to like call C3 and try to prove it for you. And yeah, it's a bit more focused on imperative programs. But yeah, maybe. Yeah.
So it's another formal language.
Yeah, right.
Designed for machine.
Right. Yeah, and in principle, ideally, in a future where AI writes millions of lines of code for us, we would have some sort of guarantee that it's doing the right thing, right? So if it's writing something in Lean or in Daphne, you could hope that humans could look at the specification and then say, okay, I trust that that's what I wanted, right? Don't have to check the code itself. But okay, so here's one goal for this project. Can we just generate a complete verified program. So the ideas for the programs themselves, specifications and proofs and so on at scale for training these systems. And essentially we set up this system that starts from random readmes from GitHub repositories, and then puts these several LLM agents to interact by writing ideas for specifications that you could formalize about those readmes, trying to implement them in Daphne, try to fix programs that are broken. If you get a working program, great, try to make it more complicated, extend it, and so on. And we have this distributed agenda that sorts these tasks and objects. And we have the system that, yeah, if you just let it run, it will keep generating programs by this combination. So we ran this for around a week after it's been set up on a prototype, and you get a graph that looks like this. For as much compute as you want, you can get more and more programs.
When was this?
Huh?
When did you carry out this experiment?
Less than a month ago. Yeah, so it's pretty recent. So we have a super recent data set of Daphne programs that's on Hugging Face that has 80,000 programs compared to all of the Daphne programs that have been collected on GitHub from people are amount to like less than 800. Yeah, so that's a lot of examples of assertions, looping variants, and so on. That in terms of volume, at least is a lot more than in human-written data sets. Here's just one example of this process. You can take a random repository that says something about some Microsoft software and not super sure, but then the idea generator will kind of sketch something related to that in Daphne and then extend it, and you get this long program that will apply diffs.
You managed to get a good sense on how many of the verified programs do what was actually in the READMEs?
Yeah, that's a good question. They're definitely inspired by the README, but generally they don't do what the README says the original program does. That's usually too ambitious for verification.
There is no rigorous way to do it.
Yeah, right.
You can have the LLM judge or something.
Right.
Human being has to decide.
Mhm.
Mandate to know.
Yeah, so this is like very much ongoing work. We have some initial good results on training smaller models on these programs and seeing if they can actually get up to speed. So for example, in Daphne you can have lemmas as well, so you can frame this task of if I remove the proof of the lemma, can a model go and go back and prove the lemma? And we can get small models like Qwen3 Coder to actually beat Claude in proving Daphne lemmas. Probably because, at least in one shot, like Claude is pretty good if you let it run for a while. But yeah, so this is promising that this is at least useful training data. But there's still a lot of challenge in generating diverse and kind of complex queries. Like most of the specifications stand up like by various complexity metrics, much simpler than the specifications in Daphne Bench, for example, which are human written. So you can get lots of programs. It's still a question of how to get interesting, complex, logically diverse programs. But assuming you can solve that, I think there's a pretty good path for synthetic data generation to overcome this recurrent problem of like, oh, we don't have that much data for this task or that task. Informal reasoning, at least. Yes, so okay, so we've talked about theory building by this view of compression, and theory building by can just make up theories using generative models, and that's at least useful for training AI. And yeah, and I think this is interesting because new mathematics can definitely come from asking for more, right? Like solve more problems. Hey AI, can you prove this that I couldn't prove myself? It's really hard. But also, I think new interesting mathematics also comes from asking for less, right? Like, okay, I know all of this to be true, but it's so complicated. Can you like find an easier way to do this? And yeah, so far we've been using like proof length and size as proxies for the complexity, but that's not quite right? But there's still a question of what is then, right? Like what are good metrics for what complexity is here? And also in this talk and for most of what I've done, we've been talking about building theories about things that we know for a fact, right? Like I proved this theorem, it's definitely true. but I'm also very interested in what this empirical theory building looks like. Like I played chess, and I've observed these patterns, like I make a hypothesis, but I can't be super sure that like this is the right thing to do. But we also build theories about those, so it would be interesting as well. So yeah, thanks so much for listening.
Got a lot of data that we want to.
Yeah. No, they're great questions. Appreciate it.
Let's thank the speaker again.
Yeah.